Now I want to give you just a little overview of where we're going to go in this class. Excuse me, a little outline of how this class is structured. So class overview. Um, and I want to start with a question. What makes dynamics trickier than statics? Because, why do we break these up into two pieces? If all we were doing is putting MA on the right side of Newton's second law and an I alpha on the right side of the rotational equation, it doesn't seem like it would make that much sense to break it up into two pieces. That doesn't seem too complicated. So that's sort of my question. Don't we just put a MA or a I alpha on the right side of Newton's second law and rotational Newton's second law? Well, no, it gets a little more complicated than that. And there are really two reasons. So two reasons it's not quite that simple. The first is that, remember, mass times acceleration is mass times the second derivative of the position with respect to time. And I alpha is I times the derivative of the angular velocity with respect to time. So Newton's second law and the rotational equation become ordinary differential equations. Okay, so we've already talked a little bit about ordinary differential equations, and that just complicates the math a little bit. Now, everything goes from being algebraic equations to being differential equations. The other thing that happens is, now that things are moving around, it's not as automatic to choose a coordinate system, because things can be moving in different ways. Do you fix a coordinate system to the ground, or do you fix it to one of the bodies, or so now choosing the coordinate system isn't as automatic as it was in statics. And sometimes the problems are easier if you choose a non-inertial coordinate system. Okay, so non-inertial coordinate systems, you have to be careful about how you apply Newton's laws. Newton's laws only hold in an inertial coordinate system. But there's something else going on too. It's not just that Newton's laws don't apply in non-inertial coordinate systems. And to make sense out of that, we're going to have to break this up into the two possible ways that you can have a non-inertial coordinate system. So one way is you can have an accelerating origin of your coordinate system. It turns out that's pretty easy to deal with. And we'll deal with that just using relative motion equations. But the other thing that can make a coordinate system non-inertial is that you can have rotating axes. That one makes things a little bit trickier. And because of that, we're going to break this class pretty much into problems where the coordinate axes are not rotating, and then problems where the coordinate axes are rotating. And so I want to, we'll revisit this when it's time to do problems with rotating coordinate systems. But I want to first, like right at the beginning, just give you a first glance at why this causes a problem. What it does is it makes our derivative relationships more complicated. Okay, so like these relationships saying that acceleration is the second derivative of position with respect to time, those kind of ones become more complicated. And I want to give you an example that can start to, help you clarify why this is, because it's an important thing to understand. Okay, so why do rotating coordinate systems affect derivative relationships? And I'm going to just give you an example. And this example, I don't even know if this is a real thing, but in movies about astronauts, they're always on these contraptions, training for, dealing with big G-forces and stuff, where they're sitting in a chair on the end of a long arm, and this arm is spinning around. And so here's the astronaut in training, sitting on this chair, trying to hold on. Okay. And okay, so there's the chair. And the chair is moving around in a circle. Okay. And so you get this big centripetal acceleration. And let's say that our coordinate system is going to have the x-axis in the opposite direction from the axis, the rotating axis, as the person. So that's x. Let's say, I don't think that is what we want. Okay, so actually let's say we have x that way, opposite the person, y this way, and z, if you're looking from the top, that's going to be out of the plane. And let's say that this length is 10 meters. That makes this person about 12 feet tall. That's about right. And we're going to, so we're going to calculate the velocity vector using a difference formula. We're going to approximate the velocity vector. Using two coordinate systems. One is non-rotating, and one is rotating. Okay, so first, case one, let's do non-rotating. This is the one we're most used to. So if this is a top view, let's look at 2 moments. Let's say this is our coordinate system, x and y, and we're going to look at instant 1 here and instant 2 here, and let's say that there's an elapsed time of 0.01 seconds between those two. Okay, so if that arm is 10 meters, then, you know, depending on what the angle is that they're going through, position 1 as a vector in that coordinate system, you know, it's a little bit, it's a big negative x, a little positive y. Let's say that this is negative 9.962 and positive 0.872. And those positions are in meters. And let's say the second one, position 2, is again negative 9.962, and this time negative 0.872. And to approximate the velocity, we're going to just do the change in position over the change in time. So we get the vector negative 9.962, negative 0.872, minus the vector negative 9.962, this time the y, so for position 1, the y component is positive 0.872. The elapsed time is 0.01 seconds. And so we get a vector of, remember this is just an approximation, but we get a vector of 0, negative 174.4 meters per second. And, you know, that's a sensible approximation of our velocity vector. We know that when the person is here, the velocity should be tangent to the circle. If it's rotating this way, it's going to be down. So that makes sense, right? So now let's look at what our measurements give us if we have a rotating coordinate system. And you'll see that this difference formula does not give us a good approximation of the velocity vector. Okay, so this time, again, we're looking at a top view. So the motion is the same, but this time, let's say, and we're going to, you know, look at these same 2 points. So this is location 1, and this is location 2. Okay, imagine those are identical to the other case. But this time the coordinate system is going to rotate with the chair, with the astronaut. So when the astronaut's in this position, we're looking at this coordinate system. And when the astronaut is in this position, we're looking at this coordinate system. Okay. In both cases, if you look at this, you can see, like, in these coordinate systems, in the blue coordinate system, what's the position 1? So this is, the blue is P1, the red is P2. Well, P1, it's just in the negative x direction of that blue coordinate system. So we have negative 10, 0. And P2, even though the point is moved, the coordinate system is rotated. So P2 ends up being the same thing, negative x direction, 10 meters. And so measured in this coordinate system, our change in position, our difference formula, divided by the elapsed time, is negative 10, 0, minus negative 10, 0, divided by 0.01, and we get a value of 0, 0. And that's not a good approximation for the velocity vector. You know, he's moving 174 meters per second. And it's not just a relative motion thing because our origin isn't moving. So we're going to have to deal with this fact that when you use time derivatives in rotating coordinate systems, you have to treat them differently than you do in non-rotating coordinate systems. So the bottom line for rotating coordinate systems, you're going to have to deal with derivatives differently. So that was meant to be just an intuitive physical explanation of why this happens. There's also a mathematical explanation, and it came up when I was talking about the chain rule. No, sorry, the product rule. So due to the product rule, say that you have, you know, your position vector is equal to your x component of the position times the unit vector I, plus your y component of the position times your unit vector j. And so p dot, which is your velocity, is equal to p x dot times I plus px times I dot plus py dot times j plus py times j dot. And these two terms are the things that don't show up in derivatives the way that we're used to doing vector derivatives. And these two terms are what are going to change our calculations when we go to rotating coordinate systems. Okay, so here's just a rough outline of the topics that we're going to discuss and the order that we're going to do it. We're going to first talk about things in terms of non-rotating coordinate systems. And again, the thing that can be a little confusing here is we still can deal with non-inertial coordinate systems, but we just deal with those using relative motion. It's fairly easy to deal with that, as long as the coordinate axes aren't rotating. So we're going to go through, this is basically the order you did in Physics 1. We're going to talk about particle kinematics, particle kinetics, then we're going to go into rigid body kinematics, rigid body kinetics. Then remember, you know, like this is really the order that we did statics. After we talk about rigid body kinetics, we talk about combining rigid bodies. In statics, it was into structures. When those things that are like structures, rigid bodies connected by joints, are moving, we call them linkages. So we'll go on to doing calculations for linkages. And then finally, we'll talk about energy methods for linkages. And again, in statics, that's what we did at the end. We talked about virtual work. That was an energy method, and now we're going to use sort of a similar approach to dealing with linkages. After we're done with this, we're finally going to get to rotating coordinate systems. And we're not going to do as much with rotating coordinate systems as we did with non-rotating coordinate systems. But we are going to deal with particle kinematics, and particle kinetics. So that's an outline of the broad topics that we're going to deal with in this class. You know, each of those topics has sort of subtopics and things, but this is a good thing to keep in mind as we go forward.